Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Quickly let me know in the chats with the thumbs ups. Quickly, my dear students. Let me know in the chats if all of you can hear me properly, if I'm perfectly audible and visible to every one of you. Yeah? All clear? All clear, guys? Perfect. So, as you all must be knowing, today we are starting one more chapter since we are done with the electrochemistry, right, which was completed in 4 sessions. And today we shall be starting the new chapter, and this new chapter is going to be atomic structure, right? Atomic structure. And my dear students, this particular chapter, since it's again one big chapter basically, so I'll be completing this particular chapter exactly in 3 sessions. 3 sessions I'll take to complete this particular chapter. Why 3 sessions? Because every single thing, I'll be starting from the scratch itself. I'll be starting from the basics itself, right? So every single thing I'll be starting from the basics exactly. So I'll be taking completely 3 sessions to finish this particular chapter, right? Perfect. So people, are you all ready for it? Are you all ready for it? Are you all ready for it? Let me know quickly. Are you all ready for it? Let me know in the chats quickly. Yeah? Perfect, guys. Perfect. So let me first of all tell you, like when all I'll be taking these 3 sessions. So first of all, today is going to be atomic structure part 1, right? That is today. Atomic structure part 2, I'll be taking on Saturday, 6 p.m. That is the part 2. And part 3, I'll be taking on Monday. On Monday, 6 p.m. So mark these dates in these 3 sessions. One is today, one is on Saturday, and one is on Monday. So 3 sessions are enough to complete this particular chapter in detail, right? And my dear students, whatever things I'll be writing on the screen, I would want everyone to take a note of every single thing. Because every single thing, whatever I'm going to let you know in the session, every single thing is going to be very important. Okay? And before starting the session, the ones who have not liked the session yet, I would want every one of you to like the session. I want the like count to increase right now. And at the same time, if you have not subscribed to this Unacademy NEET English yet, I would want every one of you to subscribe to your Unacademy NEET English channel as well. Okay? Perfect. All right, people. So let's get going then. Let's get started with the atomic structure part 1. Okay. The first topic which we are going to start. As I told you, everything will be started from the basics, right? So I'll be exactly starting from the basics itself. So the first topic which we are going to cover right now, that is going to be your cathode ray experiment. That is going to be your cathode ray experiment. So first of all, who performed exactly this particular experiment? This cathode ray experiment, which I'm going to teach you right now, it was performed by J.J. Thomson. It was performed by J.J. Thomson. And let me tell you, it was performed in 1897, right? Mark the date as well. And my dear students, with the help of this particular experiment, what exactly was discovered? With the help of this particular experiment, electron was exactly discovered, right? So with the help of this cathode ray experiment performed by J.J. Thomson, right, in 1897, what we discovered exactly? We discovered electron. Now the point is how this electron was discovered, what exactly was observed, what exactly was concluded, right? So step by step, we'll see the things. So my dear students, in this cathode ray experiment, what exactly was done? Let me tell you, a narrow glass tube was taken. Imagine this is one narrow glass tube. This is a narrow glass tube which was about 60 centimeters long. A narrow glass tube which was about 60 centimeters long was taken, right? Now, my dear students, over here in this glass tube, in this narrow glass tube, a vacuum pump was also fixed. What was the need of this vacuum pump? This vacuum pump was used to control the pressure of the gas inside this particular container. This is a particular container. This is a narrow glass tube which is about 60 centimeters long. And in this narrow glass tube, what you will find? You will find a vacuum pump which is fitted to this particular tube. What is the use of this vacuum pump? My dear students, the gas which I'm going to keep inside this container, the gas which I'm going to keep inside this narrow tube, to control the pressure, to increase or decrease the pressure of that gas inside the tube, a vacuum pump was used over here, right? And my dear students, which gas we are going to take over here? Let me tell you, it is the H2 gas which we are going to take in this particular container, in this particular narrow tube, right? And at the same time, I'll be using two metal strips. This is strip number 1. This is metal strip 2. And let me tell you, these metal strips which I'm using over here, these metal strips I'm connecting with the high voltage battery. These metal strips I'm connecting with the high voltage battery. This is a very, very high voltage battery. It is a very, very high voltage battery which I have taken over here. Now, my dear students, that metal strip which is connected with the negative terminal of the battery, that metal strip which will be connected with the negative terminal of the battery, that will be having the negative charge on it. Similarly, that metal strip which is connected with the positive terminal of the battery, that will be definitely having positive charge on it, right? And this negatively charged metal strip over here, I'll be calling this as cathode. And this positively charged metal strip over here, I'll be calling this as anode. I'll be calling this particular metal strip carrying the positive charge, I'll be calling this as anode. And my dear students, which gas was taken over here in this container? It was H2 gas which was taken for the experiment, right? Now, first of all, this particular tube which was taken for the experiment, this particular tube is what you call as Crookes tube. This particular tube which was taken for the experiment, this is something which you call as Crookes tube. Now, my dear students, what exactly were the observations? What exactly were the observations made by J.J. Thomson while carrying out this particular experiment? What he exactly did? He took H2 gas in this particular chamber, H2 gas in this particular glass tube, right? He used a high voltage battery. My dear students, when the voltage of the battery was kept 10 raised power 4 volts. When the voltage of the battery was kept 10 raised power 4 volts. When 10 raised power 4 volt battery was introduced. And when the pressure of the gas was kept very low, there were some observations. There were some observations which were made by J.J. Thomson. And what were exactly the observations? Try to understand. Before letting you know the observations, let me tell you, this particular side of the glass tube, it was coated with zinc sulfide. So this particular surface of this glass tube, it was coated with zinc sulfide. Why was it coated with zinc sulfide? My dear students, there is a property of zinc sulfide basically. And what is the property of the zinc sulfide? Let me tell you, for example, if this is a plate, which is coated with zinc sulfide, which is coated with zinc sulfide. My dear students, whenever any particle which has got certain mass, which is moving with velocity v, whenever any particle strikes this zinc sulfide, whenever any particle strikes this zinc sulfide screen, the point where the particle strikes, at that point, you'll find a bright spot. You'll find a bright spot. For example, there is one particle which has got certain mass. It is going to strike the zinc sulfide screen. The point where the particle strikes, a bright spot will be created. Similarly, one more particle over here, coming, striking the zinc sulfide. A bright spot is getting created. So there's a property of this zinc sulfide. What is the property? My dear students, whenever any particle having any mass strikes the zinc sulfide screen, a bright spot gets created on the zinc sulfide screen. Okay, so this particular side was coated with zinc sulfide. Point number one. Point number two, when the battery was turned on, when the voltage of the battery was used as 10 raised power 4 volts, when the pressure of the gas in the vessel, when the pressure of the gas in the container, when the pressure of the gas in the glass tube was kept very, very, very low, at that point of time, few observations were made by Thomson. And what were the observations? My dear students, what Thomson saw, Thomson observed some bright spots getting created on this particular screen. Thomson observed that some bright spots were observed on this particular screen. My dear students, if bright spots are getting observed on this particular screen, what can you conclude from that? What can you conclude? What Thomson concluded? Thomson concluded that there must be some invisible rays. There must be some invisible rays which seems to be coming from the cathode. There must be some invisible rays which seems to be coming from the cathode, and those invisible rays must be striking the zinc sulfide screen, and the point where the rays will be striking the zinc sulfide screen, there only bright spots would be getting created, right? So when the battery was turned on, when the voltage of the battery was kept 10 raised power 4 volts, when the pressure of the gas was kept very, very, very low, what happened? What happened? Some bright spots were observed on this zinc sulfide screen, which is only possible if some invisible rays are coming from cathode, right? They must be striking this zinc sulfide screen, and they must be creating bright spots on this zinc sulfide screen, right? So my dear students, point number one, the invisible rays, which seems to be, I'm using the term seems to be, right? I have no idea from where exactly they are generated. I have no idea right now. Okay, so these are some invisible rays which seems to be coming from the cathode. The invisible rays which seems to be coming from the cathode. Right? These invisible rays were called as cathode rays. So first of all, this is how your cathode rays were discovered. Perfect. Now, after the discovery of these cathode rays, it was important to understand the properties of these cathode rays, right? It was important to understand the properties of cathode rays, right? What these cathode rays are made up of, right? All these things now we are going to discuss basically. Okay, so first of all, the introduction of cathode rays is done. This is how your cathode rays were introduced. This is how your cathode rays were discovered. Now it was the time to check the properties of these cathode rays. Now, my dear students, a lot of things were done to understand the properties of the cathode rays. Okay, the first point was whether these cathode rays, which seems to be coming from the cathode, whether these cathode rays travel in straight lines, whether they follow the parabolic path, hyperbolic path. What was the path exactly? What was the trajectory of these cathode rays? This was the first point of discussion. And my dear students, in order to check whether the cathode rays were traveling in straight lines, whether they were following the parabolic path, etc., etc., what exactly was done? Let me tell you, an object was introduced here. An object was kept here. An object. This is the object. Right? And just behind the object, a screen was kept. A screen. right? Just behind the object, I would say, just behind the object, a screen was kept. And my dear students, on this particular screen, what you'll find? On this particular screen, what did he exactly find out? Let's try to understand. This is the object, and this is the screen basically over here. Now, when he kept the object here, and just behind the object, there was a screen placed, and again he kept the battery on, he turned the battery on, he gave the voltage of 10 raised power 4 volts, right? He kept the pressure of the gas very low. What he exactly observed? He observed a sharp image of the object was getting created on this screen. On this particular screen, a sharp image of this particular object was getting created. When is it possible? When is it possible? My dear students, if I ask you, when a sharp image of the object will be getting created on the screen, it is only possible if these cathode rays, which seems to be coming from the cathode, if they travel in the straight lines. So the first conclusion which was made by Thomson, what was that? That is your cathode rays, they travel in straight lines. They travel in straight lines. Point number one. Now, after getting to know that the cathode rays, they travel in straight line, now it was important to understand of what particles these cathode rays are made up of. Are these cathode rays made up of particles which have got some mass, which has got some charge, right? Now the second point of discussion is what these cathode rays exactly are made up of. Okay, the first point is your cathode rays, they travel in straight lines. That was point number one, right? Point number two, your cathode rays are made up of what? Now it was the point of discussion. So what he exactly did, what Thomson exactly did, he kept, let me tell you, he kept a light paddle wheel over here. A light paddle wheel was kept here. A light paddle wheel was kept over here, right? Imagine this is the stand on which a light paddle wheel was kept, right? And this paddle wheel, it was made up of a very light element, that is mica, right? This paddle wheel was made up of mica. Now, my dear students, when he kept the light paddle wheel over here, what he exactly observed? He again turned the battery on, again kept the pressure of the gas very low. What he observed? He observed this paddle wheel started to rotate. When is that possible? When this paddle wheel will go to rotate? My dear students, I would say this paddle wheel will only rotate if some particles of certain mass are striking this, right? Perfect. When some particles carrying certain mass will be striking this paddle wheel, right? Those particles which are striking this paddle wheel, they'll be imparting momentum to this paddle wheel, which makes this paddle wheel to rotate. So what he concluded from here? When he kept a light paddle wheel made up of mica inside this discharge tube, what he observed? He observed this paddle wheel started to rotate, and he concluded the cathode rays which seems to be coming from the cathode, they are definitely made up of some material particles which carry certain mass. And those particles are basically striking this paddle wheel and making this paddle wheel to rotate. Right, my dear students? So the next point is your cathode rays. Your cathode rays are made up of what? Your cathode rays are made up of material particles. Your cathode rays are made up of some material particles which have got some mass. So one more thing was concluded. First conclusion was the cathode rays are made up of what? The cathode rays are made up of material particles. And the material particles of which cathode rays are made up of, let me tell you, those material particles carry certain mass. They have got some mass as well, right? Now, my dear students, after getting to know that the cathode rays are made up of material particles, now it was important to understand the material particles of which cathode rays are made up of, whether those material particles carry certain charge or not. It was important. You must be knowing one thing. You would have studied it as well. Imagine this is a magnet. Imagine this is a magnet, for example, right? This magnet will be having some magnetic field associated with it, right? This magnet will be definitely having some magnetic field associated with it. My dear students, you must be knowing when a charged particle passes through the magnetic field, when the charged particle passes through the magnetic field, it deviates its path basically. Its path gets deviated. My dear students, this particle, it was supposed to go in a straight line, but in presence of magnetic field, it will deviate its path. Its path will get changed, right? Its path will get changed. Its trajectory will get changed in presence of magnetic field. Now, what Thomson exactly did, he kept a magnet over here. He kept a magnet over here. If magnet was placed over here, that means this particular magnet will be having definitely some magnetic field associated with it, right? It will be having some magnetic field associated with it. And my dear students, what he observed, when he again turned the battery on, when he gave the potential of 10 raised power 4 volts, when the pressure of the gas was kept very low, he observed these cathode rays, which were supposed to travel in the straight lines, these cathode rays were being deflected, right? He observed these cathode rays were being deflected. And this time, I would say, this part of the zinc sulfide was glowing. This part of the zinc sulfide was glowing. What does that mean? That means the cathode rays are striking the zinc sulfide over here at the bottom, which is only possible if these rays, if they have deviated their path and they are striking the zinc sulfide screen at the bottom. When is it possible? When is it possible, my dear students? It is possible only if the cathode rays are made up of some material particles. Those material particles will be carrying certain charge as well, right? They'll be carrying certain charge as well. That's why these cathode rays were being deflected from their original paths, right? So what was the conclusion from here? The conclusion was the material particles. The conclusion was like this. Just a second, guys. Let me tell you few more properties. The material particles of which these cathode rays were made up of. The material particles of which these cathode rays are made up of carry certain charge. Right? Now there was one more thing which was to be understood. Since we got to know that the material particles of which these cathode rays are made up of, they carry certain charge. Now it was important to understand whether the charge carried by the material particles, whether that charge was positive or negative. How did he check that? What he exactly did, he took two metal strips again. And these metal strips were connected with some different battery, some other battery. These metal strips, they were connected with some different battery, some external battery. Imagine this particular metal strip, it is connected with the positive terminal of the external battery. So this metal strip will be getting positive charge. And this metal strip, imagine this is connected with the negative terminal of the battery. So it will be getting negative charge. And my dear students, what he observed, when he again kept the voltage of this battery as 10 raised power 4 volts, so when the pressure of the gas again was kept very low, he observed these cathode rays were being deflected towards the positively charged plate. Now tell me, when is that possible? When these cathode rays will start deflecting towards the positively charged plate? Since unlikes attract. So I would say these cathode rays, they are basically made up of those material particles which carry the negative charge. That's why these cathode rays, they are deflected towards the positively charged plate. As simple as that. So my dear students, what he observed, he concluded basically the material particles of which cathode rays are made up of carry certain charge. I would say carry negative charge. And let me tell you, and these negatively charged particles, of which your cathode rays are made up of. These negatively charged particles were termed as negatrons, right? So initially it was not electron. Initially it was the negatron, right? After the discovery of, right, when this experiment was carried out, what Thomson observed? He observed some of the invisible rays, which seems to be coming from the cathode. They were made up of some material particles which have got certain mass, which have got negative charge, and those negatively charged particles of which your cathode rays are exactly made up of. He called them as negatrons. And later on, the name negatrons was changed to electron. The name negatron was changed into electron. And who changed the name? There was one more scientist whose name was Stoney. Stoney was the scientist basically who changed the name from negatron to electron, right? Did you get to know how this electron exactly was discovered? Exactly, negatron sounds cooler, right? I know. But dear students, is it clear till here? Did you get to know how this electron was exactly discovered? Yeah? Perfect. Perfect, guys, perfect. Now, from this particular experiment, few more conclusions were made. Point number one. It was observed that when these cathode rays, when they strike a heavy metal like tungsten, it was observed that when these cathode rays, when they strike a heavy element like tungsten, X-rays were produced. This was one more conclusion. This was one more observation basically. So let me write it over here. When cathode rays strike with the heavy element, like tungsten, X-rays were produced. X-rays were produced. This was one more observation and conclusion made by Thomson, right? Okay. Now, my dear students, at the same time, it was observed that these cathode rays, they produce heating effect. Right? So basically, when these cathode rays were made to fall a metal strip, were made to fall on the metal strip, it was observed that that metal strip was getting time. Its temperature was raising with time, which is only possible if these cathode rays, they produce a heating effect. Right? Perfect. I hope all these things are absolutely clear till here. So my dear students, let me conclude. Conclusion is like this. So first of all, a Crookes tube was taken which was approximately 60 centimeters long, right? And in this particular Crookes tube, H2 gas was introduced. Okay. A vacuum pump was used to control the pressure of the gas inside this container. Two metal strips were used, right? One connected with the negative terminal of the battery, one connected with the positive terminal of the battery. Negatively charged plate was called as your cathode, positively charged was called as anode, right? When the battery was turned on, when the voltage of the battery was kept approximately 10 raised power 4 volts, some invisible rays, they seems to be coming from the cathode and striking the zinc sulfide screen, at which bright spots were getting created. And he called these invisible rays as what? He called these invisible rays as the cathode rays. Now these cathode rays, they are made up of some material particles which carry certain mass, which have got the negative charge, and the negatively charged particles of which these cathode rays are made up of, he called them as negatrons. And later on, these negatrons were called as electrons. And who changed the name? It was the Stoney who changed the name from negatrons to electrons, right? And these cathode rays, when they strike the heavy metal like tungsten, X-rays were produced, right? And my dear students, at the same time, when you make these cathode rays to fall on the metal plate, what happened to the temperature of the metal plate? Temperature of the metal plate, it kept on increasing, right? Which is possible only if these cathode rays, if they show heating effect. I hope this particular thing is clear till here, right? I hope all these things are absolutely clear till here. Right, my dear students? Now try to understand few more things. Try to understand few more things. Try to understand few more things. Just have a look. Just have a look. My dear students, one more conclusion was made from here. What was the conclusion? Since after the discovery of cathode rays, it was important to know exactly what is the source of these cathode rays, from where these cathode rays are coming, right? Right? And if you ask me from where these cathode rays are coming, my dear students, the answer is very simple. Which gas did I keep inside this particular chamber? It was H2 gas. So basically, in this particular chamber, you have got H2 molecules. So these are H2 molecules basically. These are H2 molecules basically inside this glass tube. Now, dear students, when the voltage was kept high, when the pressure is kept low, what happens to these gas molecules? These gas molecules ionize. These gas molecules ionize. Since you must be knowing, if you have got one hydrogen atom, it contains one electron, one proton, right? When this hydrogen atom ionizes, right? That means when one electron is taken out of hydrogen, it gets converted into H positive. But you have got hydrogen molecule here, you have got H2 molecule over here. So can I say due to ionization, this H2 molecule would have lost 2 electrons and would have got converted into 2 times H positive. Agreed? Do you agree with this? So basically the H2 gas molecules which were there in the container, since you are keeping the voltage of the battery very high, you are keeping the pressure of the gas very low, what happens to the gas inside the container? It ionizes. It loses electrons. So basically inside this chamber, you won't find H2 molecules. Those H2 molecules have got ionized. They have got converted into what? They have got converted into H positives. And with H positives, you have got millions of electrons as well here. Right? Now, my dear students, try to understand. In this particular chamber, what do we have? Can I say in this particular chamber, due to the ionization of the gas, can I say there are positively charged and negatively charged ions? There are positively charged and negatively charged ions and negatively charged electrons here in this particular chamber. Absolutely. Right? Since this particular electrode, this particular plate, it carries the positive charge. If it carries the positive charge, can I say this positively charged plate, it is going to attract all the electrons which are there in the chamber. It will attract all the electrons towards itself, right? Perfect. It is going to attract all the electrons towards itself. And when all the electrons are moving towards this positively charged plate, can I say these electrons will be moving in the streamlines basically? They'll be moving in the streamlines. And those streamlines, those rays which are made up of these electrons, which are moving towards this positively charged plate, those rays only are called as your cathode rays. So if I ask you from now onwards, if I ask you whether cathode rays are originated from cathode, no, they are originated from the gas which is there in the container. Right? When the gas gets ionized, it gives the electrons, and those electrons basically they start moving. Yeah? Perfect? So, one important point, your cathode rays, they originate from the gas which is there in this particular chamber. I hope this particular point is also clear to you. Okay, so I will say cathode rays do not originate. They do not originate from cathode. They do not originate from cathode, but from the ionization, of the gas in the tube. Perfect. I believe this is also clear to you. Now, my dear students, one more important thing. Since you know now cathode rays which are made up of these negatively charged particles, if you ask me, how do we calculate the velocity with which these cathode rays move, right? How do we exactly get to know the velocity with which these cathode rays exactly move, right? Now, let me tell you how the velocity of cathode rays was exactly calculated. Since, my dear students, these are the cathode rays basically which are traveling, right? Now, with what velocity these cathode rays are traveling, basically? How exactly this was checked? How exactly this was calculated? For that purpose, let me teach you a bit of physics, which I'm sure you all must be knowing. My dear students, imagine that this is the positively charged plate and this is the negatively charged plate. Imagine these are the two plates which are connected to the external battery, right? Imagine this particular plate is connected with the positive terminal. This particular plate is connected with the negative terminal. That is the reason why this got positive, why this got negative. Now, for example, this is the electron. This is the electron, for example, carrying the negative charge. If the electron starts moving, so first of all, between these plates, what will be there? And I said between these plates, there will be electric field lines, right? There will be electric field lines between these two plates. Absolutely. So there is electric field basically between these plates. And my dear students, when this negatively charged particle, it passes through this particular field, what happens basically? I say this positively charged plate is going to attract this negatively charged electron towards itself. So electron will deviate its path. It will start going towards the positively charged plate. So can I basically say it like this? When the electron is traveling in this electric field, can I say the electron has to go forward basically. It has to go forward. But in this direction, the electron is experiencing a force which you call as electrical force, right? Electron, it basically has to go straight. But due to electric field, it deviates its path. Why is that? Because when the electron enters the electric field, the electron is supposed to go this way. But at the same time, this particular electron, it experiences force in this direction, right? It was supposed to go like this, but there is one more force pulling it towards itself. That's why it deviates its path due to electric field. Perfect. Now, for example, imagine if I put a magnet also here. I'm placing a magnet in such a way that the electron, when it passes, right? It experiences one more force, downward force. Due to this downward force, the electron has to go in this direction. It has to deviate in this direction. Perfect. My dear students, understand one thing. In presence of electric field, the path of the electron should be like this. In presence of magnetic field, the electron path should be like this. So basically, when the electron is simultaneously entering into electric and magnetic field, I'll say this electron is experiencing two forces. Electron has to go in this direction, but simultaneously electron is experiencing two forces. One is electrical force in upward direction, one is magnetic force in downward direction, right? Now you tell me one thing. Since I'm telling you the electron is entering simultaneously in both the fields. Due to electric field, electron is experiencing a force in upward direction. Due to magnetic field, the electron is experiencing a force in downward direction. My dear students, imagine if electric force is more than that of magnetic force, the electron will go up, right? If magnetic force is more than that of electric force, the electron, it will deviate downwards. But if we exactly balance the two forces, if we exactly balance these two forces, can you just tell me in the chats, will the electron get deviated from its path? The electron is moving in this direction, right? When electron reaches here, it is experiencing two forces. One is upward direction, one in downward direction. One electrical force, one magnetic force. If you balance these two forces, if by chance electrical force and magnetic force on the electron becomes equal, will the electron deviate? The electron will not deviate. The electron will not deviate at all, right? So my dear students, what exactly was done? The electric field and the magnetic field simultaneously were placed inside this particular container, right? Perfect. Due to which the electron of which cathode rays are made up of. Cathode rays are made of electrons, right? The electrons, they experience two forces. Imagine one upward direction, one in downward direction. And those two forces were balanced. And when these two forces were balanced, I would say electron passed undeviated. Now you tell me, why did electron pass undeviated? Because electrical force and magnetic force on the electron, they cancelled. What is electric force all about? It is the charge on the electron multiplied by electric field, right? Perfect. What is magnetic force? Charge multiplied by velocity with which electron moves multiplied by B, right? Magnetic field intensity B. Perfect. Now, my dear students, if I ask you whether this Q gets cancelled, absolutely. So V comes out to be equal to E divided by B. Now, if you ask me what this V is the velocity with which electron moves. V is the velocity with which your cathode rays move. Perfect. B is your magnetic field, E is your electric field. Electric field strength, magnetic field strength. Okay. Perfect. So, what did we calculate from here? We are getting the velocity with which the electron moves. We are getting the velocity with which the cathode ray moves. It is coming out to be equal to E divided by B. What is this E and B? E is the electric field which was generated by those two plates. What is B? B is the magnetic field which was generated by the magnet. Right? What did we do? What did we do? Basically, we changed. We kept on changing electric field and magnetic field in such a way that the magnetic force experienced by the electron becomes equal to the electric force experienced by the electron. Right? So basically, these two values we already knew. Right? Because we were the ones, because Thomson was the one who was exactly changing the electric and magnetic field in such a way that magnetic force and electric force becomes equal. Right? And electron then passed undeviated. Perfect. So these two values already he knew. If you know electric field strength, if you know the magnetic field strength, can't you calculate velocity with which the electron moves? And it was observed that the speed, the velocity with which the electron moves, the speed with which the cathode rays moves, it was observed that it is equal to 1/10 of the velocity of light. Right? So your cathode rays, they were moving with the speed 1/10 of the velocity of light. This is one more important conclusion. My dear students, after getting to know the speed with which the cathode rays move, the speed with which these electrons, of which cathode rays are made up of, the speed with which they move, after getting to know this, there was one very, very, very important conclusion. What was that? That was calculation of specific charge. Calculation of specific charge. What is specific charge? Specific charge is called as E divided by M ratio. It was important to know the E divided by M ratio. And this E divided by M ratio was calculated with the help of this cathode ray experiment tube only. Now, what is this E by M? E is the charge on electron. Since we have only discovered the electron, we do not know what is the charge. What is the magnitude of charge on electron? We do not know exactly the mass of electron. But now you are going to get to know the E by M ratio. Combinedly, how E by M ratio of electron was calculated. Let me tell you that. Did we already calculate the velocity with which electron moves? Absolutely. The velocity with which electron moves was already calculated. That was equal to E divided by B, I believe, right? Electric field strength, magnetic field strength. This is already something which we calculated, right? V was equal to E divided by B. This was already calculated. This was already calculated. Now, it was the time to calculate charge divided by mass ratio of the electron, and how this charge by mass ratio of the electron was calculated. Try to understand this a bit more in detail. See guys, for example, this is your cathode, which was inside the discharge tube carrying negative charge. This is your anode carrying positive charge, and these two are basically connected with the external battery. You know it. Connected with the external battery. Perfect. Imagine that the voltage of this particular battery is V. Imagine that the voltage of this particular battery is V. If the voltage of this particular battery is V, that means the potential difference between these two electrodes. The potential difference between these two electrodes. That will be V. Agreed? That will be V. Now tell me one thing, guys. Imagine, just to make you understand, imagine I've got electron over here with me. Imagine that I've got electron with me. First of all, tell me, this is a positively charged plate, this is a negative charged plate. Can I say there'll be field lines? There will be electric field lines, right? So electric field is between these two plates. Absolutely. Now, if you have got electron, let's say this is the electron in my hand. For example, I'm placing electron here. I'm not leaving the electron yet. I'm placing the electron here. And I'm holding the electron. Can I say this electron in this field will be experiencing a force towards this positively charged plate. Absolutely. The electron is experiencing a force right now, right? And if I by chance leave this electron, it will move towards the positively charged plate. Yes? So let's say you're keeping electron here. When you keep the electron here, and imagine, it is hypothetical, imagine you're holding this electron. The electron will be experiencing a force in this direction. This plate will try to attract the electron towards itself. And my dear students, I'm holding the electron, but the electron would want to go towards the positively charged plate. But I'm holding the electron. That means this electron has got some potential energy right now. If I suddenly leave it, this potential energy will start getting converted into kinetic energy, right? I'm writing it over here. If the electron, or you can write in general, if the charged particle is placed under a potential difference, under the potential difference of V volts. If a charged particle is placed under the potential difference of V volts, what will happen? Can I say the potential energy of the charged particle will start getting converted into its kinetic energy, right? Perfect. What is potential energy exactly equal to? Do you know potential energy is equal to charge on the electron multiplied by potential difference between the plates, right? Q multiplied by V, that's your potential energy. Kinetic energy, half of mv square. This is the velocity of electron, this is the mass of electron, right? Perfect, guys. Now tell me one simple thing. If I would want to eliminate V square from here, they say V square will be 2 times Q, capital V, divided by M. What is the small v and capital V? Small v is the velocity with which the electron is moving. What is capital V? It is the potential difference between these two plates. It is the voltage of this particular battery, right? Now V already you know, it's E by B. So V square will be equal to E square by B square. So E square divided by B square is equal to 2 times Q, capital V, divided by M. Perfect, my dear students. Perfect. What is Q? Q is the charge on electron. What is M? M is the mass of electron. Charge on electron is represented by E, right? So if I ask you, what will be the E by M value? E divided by M will be equal to E square divided by 2 B square multiplied by capital V. Do you agree with this? E by M came out to be equal to E square divided by 2 B square multiplied by V. My dear students, already we know the E value, already we know the B value, and this voltage, this potential difference, we already know. Perfect. So all the values over here we already know. So can I say E divided by M value? We can easily calculate from here, right? E divided by M value, we can easily calculate from here. And how much it will come out to be? It will come out to be 1.76 into 10 raised power 11 coulomb per kg, right? So my dear students, with the help of this particular calculation, E divided by M ratio, specific charge of the electron, E by M ratio of the electron was calculated, and it was found out to be 1.76 into 10 raised power 11 coulomb per kg. Right? Right, people? So this is how your E by M ratio was calculated. Charge on electron was not calculated yet. Mass of electron was not calculated, but the ratio of charge and mass of electron was already calculated with the help of this particular experiment. Yeah? Now, my dear students, which gas did I take? H2 gas. Now, the experiment was repeated again with the help of one more gas. When the experiment was repeated by taking one more gas, E by M ratio was coming out to be same. When one more gas was taken, experiment was again repeated. E by M ratio was coming out to be same. Right? Because what exactly happens? All the gases will give away the same electrons during ionization, and those electrons will move. Perfect. So my dear students, let me tell you, this experiment, it was carried out many a times, and E by M ratio of electrons was coming out to be same. So what was concluded from here? It was concluded that the E by M ratio of cathode rays, I would say, the E by M ratio of cathode rays is independent. It is independent of the nature of the gas taken. It was the independent of the nature of the gas taken. And it was independent of the material of electrodes which were used. It was independent of the material of the electrodes which were used. Okay. So I hope you got to know exactly how E by M ratio of the electron was calculated, right? And my dear students, since E by M ratio was calculated, no doubt, E by M ratio was calculated. E by M ratio of electron was calculated, but the charge on electron was not calculated yet. The mass of the electron was not calculated yet individually, right? Now it was the time to calculate the exact charge present on the electron. And how exactly they calculate the charge on the electron? With the help of Millikan's oil drop experiment. Someone is asking, what is hydrogen spectrum? Bro, I did not reach the hydrogen spectrum yet. Just wait, hydrogen spectrum will be done in the second session. Okay, I'm just teaching you the basics right now. Because if your basics will be clear, this chapter entirely will be clear. Hydrogen spectrum, everything will be done in detail. Just wait for it. This is just the basics. Okay. So my dear students, E by M ratio was calculated with the help of cathode ray experiment. Now the charge present on the electron was calculated with the help of Millikan's oil drop experiment. Right? Now what this Millikan's oil drop experiment exactly is all about? With the help of Millikan's oil drop experiment, how the charge of electron was calculated. Let's get to know about that. But before knowing about that, you should know a term called as terminal velocity. Have you ever heard about terminal velocity? Do you know what terminal velocity is all about? In physics, paper 2, class 11th. Have you heard about terminal velocity? Say yes or no in the chats. Everyone. Say yes or no in the chats. Do you know about terminal velocity? I'm asking you. See, let me give you a slight idea about the terminal velocity. Then only I will be able to teach you the Millikan's oil drop experiment. Then I'll exactly show you how charge on electron was calculated. Have a look, people. Try to understand this. See, for example, I have got an object. This is the object. Its mass is m, right? Its mass is m. Let's say over here it's the ground surface. This is the ground surface. Perfect. And I have got the object over here whose mass is m. Imagine I'm holding this particular object. So what is the speed of this object right now? Its initial speed, its initial velocity is 0. Because you're holding it, right? Now, my dear students, when you drop it, what's going to happen? When you drop it, this object will start coming down. This object will fall, for example, this particular trajectory and will start coming downwards. Now, my dear students, when the object reaches a point here, for example, when the object reaches this particular point, when the object is here, can you let me know how many forces are experienced by this object right now at this particular point of time? Due to gravity, it's going to be mg. This is one force due to gravity, right? Since there is air as well, there is air as well in the atmosphere. I'll say when the object will be going downwards, this particular object will be experiencing a viscous drag as well due to air. Viscous drag as well, right? It will be experiencing viscous drag as well. It will be experiencing viscous force as well. When the object will be going downwards, first of all, at some point of time in between, it will be experiencing two forces, mg downwards and viscous drag or viscous force whose direction will be opposite to the direction of motion. If the direction of motion is downwards, so the viscous force will be upwards. Perfect. When this object will keep on going down, there will be a point at which the viscous force and weight and force due to gravity, they would have got equal. When the object is coming downwards, at some point of time, you'll observe viscous force and mg getting equal. And when the viscous force and mg gets equal, at that point of time, the net force on the electron becomes 0. Sorry, net force on this object becomes 0. This force and this force, at some point of time, if they are equalized, what happens? That means the net force experienced by this object will be 0. And my dear students, when net force experienced by the object will be 0, After that, I would say the object will start moving with the uniform speed. And that uniform speed with which the object moves, when both the forces becomes equal, when the net force on the object becomes zero, that uniform speed which the object attains when the net force on the object becomes zero, that uniform speed is something which you call as terminal velocity, terminal speed. Did you get the idea of what terminal speed is all about? Yes? Right, people? Yeah? Did you get the idea of what this terminal velocity is all about? It is the uniform speed with which the object moves when the net force on the object becomes zero. As simple as that. Now we will try to understand. Now I'm going to make you understand, since you got to know what this terminal speed, terminal velocity is all about. Now it's time to check how the charge on the electron was found. Okay. So my dear students, what exactly I'll be doing? Have a look. I'll be taking a cube over here. Try to understand. This is the cube which I've taken over here. This is the cube. Okay. Now, first of all, I'm dividing this cube into two equal parts. I'm dividing this cube into two equal parts. Perfect. Not just two equal parts. I mean, I'm dividing this cube into two parts, right? I'm dividing this cube into two parts. Okay. Now, my dear students, this particular part with which you are dividing this cube, I'm going to keep a hole at the middle of it. There is a hole at the middle of it. This is the hole at the middle of it. Right? Now. Let me tell you over here in the upper chamber, what I'm fixing here? I'm fixing an atomizer. What is the use of this atomizer? My dear students, with the help of this atomizer, we are going to spray the oil droplets in the upper half of the cube, in the upper chamber of the cube. So these are the oil droplets in the upper chamber of the cube. Okay. These are the oil droplets in the upper chamber of the cube. Now, my dear students, let me tell you one thing. Whenever you keep oil droplet in the vicinity of electrons, whenever you keep oil droplet in the vicinity of the electrons, let me tell you, these oil droplets, this particular oil droplet, it's going to attract these electrons towards itself. I would say these electrons will be adsorbed. The electrons will be accumulated on the surface of the oil droplet, right? When you keep oil droplet in the vicinity of the electrons, I'll say the oil droplet will attract the electrons towards itself, due to which all these electrons will get accumulated on the oil droplet. Now, my dear students, if the electrons are accumulated on the oil droplet, can I say oil droplet carries now the negative charge? Yes, it carries the negative charge. Yes, it carries the negative charge, right? Now we will try to understand few important things. What exactly we are going to do? In this bottom chamber, we are keeping the hydrogen gas molecules. These are your hydrogen gas molecules which are present in this chamber. These are your H2 gas molecules. Now, my dear students, in this bottom chamber, there are H2 gas molecules. So what exactly we will be doing? We'll be providing some X-rays, and these X-rays, they will be incident on these gas molecules. We'll make sure. What just happened? What just happened to the light? Can you all see me? Is it clear? Can I teach like this with the... What happened to the light? I don't know. Just a second, people. What do we do? What do we do? Light hi chali gayi. But can you see the board? I believe yes. Hope it does not go away. Just a second, guys. Just a second. Be like this. Be like this. I don't know what happened. Okay, let's go now. Let's go. Let's go. I hope it remains the same. Okay, guys. So this bottom part of the cube, it contains what? It contains H2 gas molecules. Now you are making X-rays. You are making X-rays to strike these hydrogen gas molecules. And let me tell you, when these X-rays, when they strike the hydrogen gas molecules will ionize. And you know, when hydrogen gas molecules ionize, they lead to the formation of H positives and electrons. So can I say in this bottom chamber, what you will find? You will find electrons, and with the electrons, you will find H positive ions as well. So there will be a lot of electrons present here. And from where these electrons have come? These electrons have come from the ionization of H2 gas. Okay. Now, my dear students, understand. One is asking, sir, when will you take equilibrium? Equilibrium I've already taught on this channel. Go to the playlist, find equilibrium there. Okay. All right. Now, my dear students, what is going to happen? See, in this particular chamber, there are oil droplets. In this particular chamber, there are electrons. Now, there will be a scenario. When one of the oil droplet will pass through this particular hole and will start coming downwards. Right? Will start coming downwards. A scenario will be there when one of the oil droplet will pass through this particular hole, will come in this particular chamber containing electrons. Now imagine one of the oil droplet has come, it has reached here. My dear students, when oil droplet reaches this particular chamber of the cube, can I say this oil droplet is going to attract these electrons towards itself? Due to which, what's going to happen? I'll say these electrons will be accumulated on this oil droplet, and this particular oil droplet now carries a negative charge. Right? Now I am showing this particular oil droplet right here. Try to understand. This particular oil droplet is going downwards. It's going downwards. Right? It's going downwards. Perfect. Now, my dear students, if this particular oil droplet is going downwards, can you tell me how many forces are experienced by this particular oil droplet here? How many forces are experienced by this oil droplet? This will be mg since it's going downwards. So mg, and opposite to its motion, there will be viscous force. Can I say when the oil droplet will continuously keep on coming down? Can I say a scenario will come when Fv becomes equal to mg? When this viscous force becomes equal to what? Becomes equal to mg. Perfect. At that point of time, what about the net force? Net force on this oil droplet becomes 0. And when the net force on the oil droplet becomes 0, after that this oil droplet will start moving with the uniform speed. And that uniform speed is what you call as terminal speed. And that terminal speed I'm representing with the nu1 or V1. What is V1? It is the terminal speed attained by the oil droplet. Right? I hope this is clear. So my dear students, can I say, I'll write over here. In absence of electric field, a scenario came at which viscous force became equal to mg. Right? How do you exactly calculate viscous force? Viscous force is calculated by the formula. I hope you have studied the Stokes law in physics, right? Viscous force is equal to 6 pi neta r v. 6 is constant, pi is constant. This neta is called as coefficient of viscosity. R is the radius of the oil droplet, and this V1 is the terminal velocity with which this oil droplet is moving in absence of electric field. And this particular term is equal to mg. Right? Now, my dear students, try to understand. What is this m? M is the mass of oil droplet. So, can we just do one thing? Instead of mass of oil droplet, since density is equal to mass by volume, so instead of mass of oil droplet, can I write density of oil multiplied by density is equal to mass by volume multiplied by volume of oil droplet, right? Multiplied by what? Multiplied by g. Perfect. And my dear students, just try to understand. Density of oil droplet multiplied by volume of oil droplet. Oil droplet is spherical in shape. Its volume is 4 by 3 pi r cube, right? 4 by 3 pi r cube, right? Density multiplied by volume multiplied by g. So can I say one of the r and one of the r gets cancelled out? Absolutely, right? So what can we conclude from here? This particular pi gets cancelled out. So can I calculate the value of r square from here? The value of r square. The value of r square will be equal 3, 3 6 are 18. 3, 3 6 are 18. So this 18, I got cancelled. This is 18 neta V1 divided by 3, 6, 18 neta V1 divided by what? Divided by density of oil multiplied by 4. And what is there? Multiplied by G. Perfect. So can't you calculate R from here? R will be equal. This will be 9 by 2. So under root of 9 divided by 2, this is neta, this is V1 divided by density of oil droplet multiplied by G. Well, first of all, a question can be asked from here. How do you calculate the radius of the oil droplet? How do we calculate the radius of the oil droplet? So my dear students, the radius of the oil droplet is calculated. Radius of the oil droplet is calculated over here. Now, why did I calculate this radius? Because there is a logic for it. What do I need to calculate actually? I need to calculate the charge present on the oil droplet. In absence, I have not applied any electric field yet. I'm not applied any electric field yet. In absence of electric field, I calculated the radius of the oil droplet. Perfect. Radius of the oil droplet. If you know the coefficient of viscosity, if you know the terminal speed with which the oil droplet moves, if you know the density of oil, G value you know, you can easily calculate the radius of oil droplet. Point number 1. Point number 2. What actually I'm supposed to calculate? I'm actually supposed to calculate the charge present on the oil droplet. And how exactly you're going to calculate that? Try to understand. Now, my dear students, if we just do one thing, if we connect this particular plate of the cube and this particular plate of the cube, these two plates of the cube, I'm connecting with the external battery. Let's say this is positive, this is negative. Perfect. When I connect them with the external battery, this is positive, this is negative. So this plate is connected with the positive terminal. So this particular plate, it carries the positive charge. This particular plate now carries the positive charge. And this particular plate carries the negative charge. Perfect. Now, my dear students, in presence of electric field, try to understand now. In presence of electric field, what is going to happen? In presence of electric field, what is going to happen? Try to understand. First of all, when the oil droplet comes down, it grabs the electrons. Oil droplet becomes negative charged, right? Now, my dear students, if this oil droplet is negative charge and this particular plate now is positive charge, can I say this plate is going to attract this oil droplet towards itself? Absolutely. This plate is going to attract this oil droplet towards itself. Perfect. So basically, this particular oil droplet in presence of electric field, the oil droplet which carries the negative charge, it is going downwards. So downward force is mg. And this particular plate is attracting it towards itself. So there is electric force. There is electric force experienced by this oil droplet. At the same time, just tell me one thing. If you keep on increasing the voltage of the battery, electric field between these two plates will keep on increasing. And if electric field between these plates keeps on increasing, I'll say this upward force will keep on increasing. There will be a time. If I continuously keep on increasing the voltage, the field between the plates will keep on increasing. There will be a time this FA, since it continuously keeps on increasing, due to increase in electric force, I would say there will be a scenario when this oil droplet starts going upwards. Right? This oil droplet starts going upwards at some point of time. And when the oil droplet starts going upwards, the motion is upwards. Opposite to the motion, there is viscous drag. Now the viscous drag will be downwards. Right? When the oil droplet is going upwards, how many forces are experienced by this oil droplet now? 3 forces. One is electrical force, one is mg, one is viscous force. Can I say a scenario will come when this oil droplet will keep on going upwards? Can I say a scenario will come at which the upward, downward forces would have got equalized? At that particular point of time, what will be the net force? What will be the net force on the oil droplet? That will be 0. Right? The net force on the oil droplet will be 0. And the oil droplet now will be going upwards with a constant speed. And that constant speed is what you call as terminal speed. Right? Let's assume that terminal speed right now is V2. What is V2? It is the terminal speed attained by this oil droplet going upwards in presence of electric field. So in presence of electric field, I must say FE will be equal to Fe will be equal to viscous force now plus mg. Right? Clear? Clear, guys? Now, what is Fe? It is the electrical force, which is charge multiplied by electric field, is equal. Viscous force is going to be 6 pi neta r. Should I write V1 or V2? I'll write V2. Perfect. In presence of electric field. Plus what? Plus mg. Already you know mg, it's a constant. Mg, it's a constant. M is constant, G is constant. Mg will be equal to 6 pi neta r V1. So this is 6 pi neta r V1. Perfect. Now, my dear students, if you can write something like this, QE is equal to 6 pi neta r is common. So it's going to be nu1 plus V2. What is V1 plus V2? What is V1? V1 is the terminal velocity attained by the oil droplet in absence of electric field. V2 is the terminal velocity attained by the oil droplet in presence of electric field. V1 is the terminal velocity attained by the oil droplet when it was going downwards. V2 is the terminal velocity attained by the oil droplet when it's going upwards. Clear? Clear, my dear students? So Q from here will be equal to 6 pi neta r V1 plus V2 divided by what? Divided by E. My dear students, look at all the parameters which are involved in this equation. Look at all the parameters which are involved in this particular equation. You have got a constant, coefficient of viscosity. Value already we know. Radius of the oil droplet, we already have calculated it. V1, we already know. V2, we already know. Electric field strength between these two plates with the help of this particular battery, we already know. So can't we calculate Q from here? What is Q? Q is the charge on oil droplet. And you know charge on oil droplet is due to the electrons which are present on the oil droplet. My dear students, it was observed the minimum charge present on the oil droplet was, its magnitude was 1.6 into 10 raised power minus 19 coulomb. This was the minimum charge present on the oil droplet. And the minimum charge present on the oil droplet was, sign is minus because it's electron, right? It was this much. When the same experiment was carried out one more time, the charge on the oil droplet came out to be 2 times this value. When the same experiment was carried out one more time, the charge on the oil droplet came out to be 3 times this value. Similarly, 4 times, 5 times. So it was believed that after performing this particular experiment many a times, it was believed that charge present on the object will be the integral value of this particular value. It will be the integral value of this particular value over here. This particular value, you call it as E. And it was finally believed that the charge present on any object is always the integral multiple of E. Perfect. Quantization of charge, you would have heard. Charge remains quantized. It will be the integral multiple. I hope this particular thing is clear. So you got to know how charge on oil droplet was calculated. You got to know the radius, etc., etc. So take care of these two statements. First statement. From this experiment, he calculated the minimum charge present in the oil droplet was this much. Only the magnitude wise I'm saying. And any particle, if charged, will have the charge which is equal to the integral multiple of this particular value. Right? So Q came out to be N times E over here. What is E? E is this particular thing. I hope this is clear to everyone. So, with the help of the Millikan's oil drop experiment, the charge on electron was calculated. And you got to know how exactly. Hope all these concepts are clear. Now, my dear students, if all these concepts are clear, can we solve this question? Look at the question carefully. Can we solve this question? Look at the question. Read the question carefully. Read this question carefully. As per this particular question, in an oil droplet experiment, the terminal velocity of oil droplet was this much in absence of electric field. So basically V1 is given 1 meter per second in absence of electric field and 2 meter per second upwards in presence of electric field. So V2 is given 2 meter per second in presence of electric field, right? Electric field of strength. Electric field strength is 6.75 into 10 raised power 6 pi volt per meter. right? Electric field strength. Density of oil droplet is also given. Density of oil droplet is given as 1 gram per ml. And coefficient of viscosity, neta, is given 2 into 10 raised power minus 5, right? Well, long back there was one question asked in NEET in physics. What are the dimensions of coefficient of viscosity? Can you let me know in the chats? Long back, I think in 2014 or 13, something around that. What are the dimensions of coefficient of viscosity? You can calculate it from the result. F is equal to 6 pi neta RV, right? I think it used to be M1L minus 1 T minus 1, something around that. I think so. Anyways, have a look. So neta is given. So what are we supposed to calculate? First, we are supposed to calculate the radius of oil droplet. Radius of oil droplet. Do we know the result? Do we know the result to calculate radius? R is equal to. How do we get the R value? Right now we got the R value, right? R is 9 by 2. R is under root of 9 by 2. Neta. Neta is something we know. V1 something we know. Density of oil we know. Gravity, acceleration due to gravity. This is something we know. So you can calculate R. Second is, what was second thing? So radius of oil droplet you can easily calculate. What about the second thing? The charge on the oil droplet. Charge on the oil droplet you can calculate with the help of this particular result. 6 constant, pi constant, neta you know. Radius you have calculated. V1, V2 is given. Electric field strength is given. So from here you can calculate the charge present on the oil droplet as well. Is this particular thing clear to you people? Let me know once in the chats quickly. Yes? Is it clear to you? So this is how your cathode ray experiment was done. E by M ratio was calculated and then charge on the electron through the Millikan's oil drop experiment was calculated. Now, you must have heard about the anode ray experiment as well. Have you heard about anode ray experiment? Similar type of experiment was carried out. Anode ray experiment. Anode ray experiment. It was a different scientist who did this particular experiment. What was the name of that scientist? It was Goldstein. Right? And with the help of this particular experiment, what was discovered? It was proton. Proton was discovered. That means your anode rays were discovered. Anode rays were discovered. Now you must be thinking how these anode rays were discovered. In a similar way, the way we discovered the electrons, in the similar way, we are going to discover the protons as well. Let's have a look how exactly. See guys, try to understand. The same tube I'll be taking, the same glass tube I'm taking, right, which is 60 centimeters long, you know it. You call this particular tube as the Crookes tube. Now I'll be comparatively fast, okay? You know all these things. Now over here, what do we have? We have got a vacuum pump. Why do we need this vacuum pump? To control the gas inside this particular chamber. Which gas do we use in the beginning? H2 gas, right? H2 gas. Imagine this is one of the metal strip. This is one more metal strip. Now, my dear students, one of the metal strip, you are going to connect with the negative terminal, positive, negative, positive. And over here, this positively charged. This particular strip is connected with the positive terminal of the battery. So, negatively terminal means this carries negative, this carries positive. Now, my dear students, this side of this particular glass, the other side of the glass, it is coated with zinc sulfide. It is coated with zinc sulfide. And you know the property of zinc sulfide. If any particle strikes it, glow will be there, right? Glow will be there. Perfect, people. This is something which we already know. Now, which gas is there in the container? It's H2 gas in the container. My dear students, try to understand few important things now. Since already you have taken H2 gas. Now, this is a high voltage battery. When you provide the voltage of 10 raised power 4 volts, when the pressure of the gas is very low, what is going to happen? Can I say the gas in the container, it will ionize? Absolutely, it would have ionized. Due to which, there will be positively charged ions over here. And at the same time, there will be electrons as well. Due to the ionization of the gas. We know it already, right? Yes. Now, my dear students, try to understand. Only one different thing I'm doing over here. this particular cathode which I'm using over here, I'm keeping some holes in this cathode. Some holes are kept over here. And this particular cathode I'll be calling as perforated cathode. This is your perforated cathode. And this is your normal anode. This is your normal anode. Now, my dear students, when the battery was turned on, when the voltage of the battery was given as 10 raised power 4 volts, what did Goldstein observe? He observed some bright spots got created just behind these holes, right? He observed that some bright spots got created just between these holes on the zinc sulfide screen. My dear students, what he concluded from there? What he concluded? He concluded there are some invisible rays. There are some invisible rays which seems to be coming from the anode. Crossing these holes and striking the zinc sulfide. That's the reason why these bright spots are created. And these invisible rays which seems to be coming from the anode, right? He called these invisible rays as the anode rays. So, the invisible rays which seems to be coming from the anode were called as anode rays. My dear students, and these anode rays are also called as canal rays. Why? Because when they pass through the perforated tube, when they pass through the perforated electrode, they traveled like the water in a canal travels, like a streamline, okay? You call them as the canal rays as well. Perfect. So this is how these canal rays, these anode rays were discovered. Now, my dear students, after the discovery of these anode rays, it was again important to observe, to check the properties of these anode rays. Now, it was the time to go for the properties of these anode rays. The same things were repeated. Let me show it to you directly now. The same things were repeated. Let me show it to you directly. My dear students, same things were repeated. First thing, anode rays, they travel along a straight line path because they cast shadow of the object placed in between their path. The same thing which was done there. For example, if you place an object over here, this is the object, imagine. This is the object. And behind the object, you are placing a screen. Or the screen is already placed over here. Zinc sulfide screen. Now, my dear students, this object which you are placing over here, when you turn the battery on, when you keep the voltage of the battery 10 raised power 4 volts, when you decrease the pressure of the gas, what was observed? It was observed that a sharp image of the object was created here. Which is only possible if these anode rays, if they travel in straight lines. Right? So first conclusion was done. Your anode rays, they travel in the straight lines. Point number one. Point number two, the same scenario, my dear students. Point number two. When a light paddle wheel, was kept over here, this light paddle wheel started to rotate, right? Which is only possible if the anode rays are made up of some material particles carrying certain mass, right? So this was the second conclusion. Anode rays, they rotate a light paddle wheel when placed in their path. This shows that anode rays are made up of some material particles which carry certain mass, right? Now, since it was checked that anode rays travel in straight lines, they are made up of some material particles carrying certain mass. Now, it was important to check whether they have got some charge or not. So for that purpose, a magnet was introduced. And in presence of that magnetic field, I would say anode rays, they deflected their path, which is only possible if anode rays are made up of some material particles and those material particles carry certain charge, right? So it was believed that your anode rays, they are made up of material particles and those material particles are charged. those material particles are charged. Now the point was, which charge was present on the material particle? For that, again, two plates were used, one carrying positive, one carrying negative. And these anode rays, they moved towards the negatively charged plate, right? Which is evident. Now it is evident the anode rays are made up of some material particles which have got some mass, which carry some charge. And since these anode rays are moving towards the negatively charged plate, your cathode rays, they were moving towards the positively charged plate. Here the anode rays are moving towards the negatively charged plate. From that you can conclude your anode rays are made up of some positively charged particles. So it was believed that your anode rays are made up of the positively charged particles. Perfect. Perfect, guys. And after that, these positively charged particles of which these anode rays were made up of, these positively charged particles were called as protons. Perfect. So I believe all these things are clear. These anode rays of which these positively charged, these anode rays are made up of some particles. Those particles carry certain charge. They have got some mass. They carry the positive charge, and these positively charged particles were called as protons. Right. So if I ask you what these protons exactly are, since you know hydrogen gas in the beginning it got ionized, right? Hydrogen gas in the beginning got ionized. So you got positively charged ions over here, right? And negatively charged ions, negatively charged electrons over here. Now, which positively charged ions these were? Since you had taken H2 gas, so these were your H positive ions. So these were basically the H positive ions. Which were moving towards the what? Towards the zinc sulfide. And those H positive ions were striking this surface and creating the bright spots. And this positively charged ion is basically what you call as proton. Right? So basically your anode rays, they are made up of what? They are made up of positively charged ions. And when you keep the gas as H2, that positively charged ion is basically H positive. And this H positive is something which you call as proton. What is H positive exactly? From hydrogen. In hydrogen, there is one electron, one proton. If you take one electron out, it becomes H positive. In H positive, there is no electron basically, right? It is H positive. This H positive is something which you call as proton. Perfect. Now tell me one thing. Now the point is how the velocity of these anode rays was calculated. The similar way, my dear students. The similar way. Anode rays, they were simultaneously passed in electric and magnetic field, right? Due to which these anode rays, the anode ray, what it experienced two forces. One was electric force, one is magnetic force. And those forces were balanced. FE and FB was balanced. FE was Q multiplied by E, and FB was Q multiplied by V multiplied by V. Q got cancelled. So velocity with which the anode rays move, that was calculated with this particular result. Right? That was calculated with this particular result. Velocity with which the anode rays move is equal to electric field divided by magnetic field. Perfect. Same scenario which we already did in case of cathode rays. In the similar way, the velocity with which the anode ray moves, it was also calculated. Perfect. It was also calculated. Perfect. I believe it's clear to everyone. Now, it was the time to calculate E by M ratio. How you guys are going to calculate the E by M ratio? My dear students, if a charged particle is introduced in some potential difference, its potential energy starts getting converted into kinetic energy. Already told. Potential energy is Q multiplied by V. Kinetic energy is half of mv square. Right? So V square is simply going to be equal to 2 times Q. V divided by M. V square is going to be E square upon B square. So E square upon B square is equal to 2 times Q. V divided by M. What is Q? Q is the charge on the proton. M is the mass of proton. So Q by M. Q I'm representing with E. So it is basically E by M. So E by M will be equal to what? It will be equal to E square divided by 2 times V square multiplied by capital V. Right? Now already this electric field strength, you already know. Right? Perfect. Perfect, guys. V is the potential difference between these two rods, you already know. Magnetic field strength, you already know. So E by M ratio of the anode rays was calculated. E by M ratio of proton was calculated. By knowing, since all these values were familiar, right? All these values were familiar. If you put all these values in this result, you'll easily calculate E by M ratio. And E by M ratio, with the help of this E by M ratio of anode rays was exactly calculated. Right, people? Okay? Is it clear? Is it clear? This was the calculation done, which I showed you. And let me tell you, E by M ratio of anode rays, it was found out to be this much, 9.58 in 10 raised power 7 coulomb per kg. Right? This was the E by M ratio of what? This was the E by M ratio of your anode rays containing when H2 gas was basically in the container. Now you tell me one thing. Since you took H2 gas in the beginning, perfect, and in case of H2 gas, it got ionized into H positive and electron. Those H positives then moved, formed the anode rays. Those H positives formed the anode rays basically. Right? That's something which understood. That's something which understood. And when the gas was H positive, E by M ratio came out to be this much. I guess students, if you change the gas, will the positively charged ion be same or different? Let me know. If you change the gas, will the positively charged ion in the container be same or different? When you change the gas, that gas ionizes. Perfect. The positively charged ion will be different. If the positively charged ion is different, will the E by M ratio of anode ray, will it come out to be same or different? It will come out to be different. E by M ratio will come out to be different. Listen carefully what I'm saying. Initially, I kept H2 gas, and that H2 gas that got ionized as H positive and electron. Electrons started moving in one direction. H positive ions started moving in one more direction. Electrons gave rise to cathode rays, right? And the positively charged H positives, they gave rise to anode rays. Perfect. So when you are using H2 gas, your anode rays at that point of time are made up of H positive ions. Now imagine you have used the H2 gas. Your anode rays, they are right now made up of H positive ions, right? And the E by M ratio, when you are using H2 gas, is coming out to be this much. Now you're changing the gas. If you're changing the gas, what will happen to the positively charged ions? If you change the gas, will the positive charged ions be H positives in the container? No. It depends on the gas which you have taken. Right? It depends on the gas which you have taken. So on changing the gas, these positively charged ions in the container will change. Right? So that means at that point of time, your anode rays won't be made up of H positives. They'll be made up of those cations which are coming from the gas. So on changing the gas, will the E by M ratio of anode rays be same or different? It will be different. Because this is the E by M, this is the E by M. When your anode rays are made up of H positive ions. If you change the gas, your anode rays, they will be made up of some other positively charged ions. So E by M ratio of those other positively charged ions will be different. So tell me whether E by M ratio of anode rays, whether it depends on the nature of the gas taken or not. Tell me that. Whether it depends on the nature of the gas taken or not. Yes, it does. Okay. So do remember the nature of anode rays. That is if I talk about E by M ratio of anode rays, it depends on the nature of the gas taken, number one. Number two, it depends on the material of which electrode is made up of. That too. Okay? That too. Now, since you have calculated E by M ratio of anode rays, now it was the time to calculate. It was the time to calculate. What? To calculate some other things. Just a second. Just a second, guys. Just a second. It was the time, since E by M ratio of electron was calculated, right? Charge on electron was also calculated. Perfect. If E by M ratio of electron you know, charge on electron you know, mass of electron can be easily calculated, right? I'm talking about cathode rays. E by M ratio of electron you already know. The charge present on electron you already calculated with the help of Millikan's oil drop experiment. So mass of electron can be calculated. In the similar way, mass of proton can be also calculated. Imagine that you have taken H2 gas in the container. So your anode rays are right now made up of H positive ions. And for this H positive E by M ratio, we already know. How much is that? E by M ratio is equal to this much. Right? Now, charge on proton is 1.6 in 10 raised to the minus 19 divided by mass of proton is equal to this much. So from here, your mass of proton was calculated. Perfect. So mass of proton came out to be 1.67 into 10 raised to the minus 27 kg. So E by M ratio for particles constituting the anode rays, it depends on what? It depends on the nature of gas taken. Because if you change the gas, this cation keeps on changing, right? This cation keeps on changing. I believe this is clear to everyone. Perfect, guys. Now there are some conclusions at the end which you have to remember, and I want you guys to remember these conclusions. See, let me quickly recap things. So first of all, cathode ray experiment was done through which electrons were discovered. From the same experiment, E by M ratio of electron was calculated. Through Millikan's oil drop experiment, charge on electron was calculated. E by M ratio we know for the electron. Charge we have calculated. So mass of electron was calculated then, right? Similarly, in case of anode rays, anode rays when the gas is H2. Perfect. Anode rays when the gas is H2. First, E by M ratio of anode rays was calculated. Number one. Number two, charge of the protons which form the anode rays, it was calculated. After that, mass of proton was calculated. Perfect. And all these things are written over here. Mass of electron came out to be this much, right? Charge on electron. Perfect. Mass of proton, right? This particular result is important. Mass of proton is 1837 times mass of electron. Charge of proton is 1.6 into 10 raised to the minus 19 coulombs. Perfect. So do remember these 3-4 points over here. These are important. Perfect, guys. Is this clear to everyone? Any doubt till here? Any doubt till here? Tell me in the chats quickly. Tell me in the chats quickly. Now, there was discovery of neutron as well. How neutron was discovered? It's a very simple thing. This is something which you are not supposed to go into the details, right? See, guys. Neutron was discovered by Chadwick, first of all. He performed some scattering experiment in which he bombarded some light elements like beryllium and boron with the fast-moving alpha particles. Now, first of all, what are alpha particles exactly? Right? What are alpha particles exactly? See, for example, you take helium atom. Atomic number 2, mass number 4. In helium atom, you have got 2 electrons. If you take these 2 electrons out, it will get converted into He di positive, right? So this He di positive is something which I call as helium nuclei. This is something which I call as helium nucleus because it does not contain any electron now. Initially, it had 2 electrons. Now you have taken those 2 electrons out. Now no electron in He di positive. So this helium nucleus now, it is only helium nucleus, right? This is nucleus of helium and there are no electrons. So this is helium nucleus. This helium nucleus is something which you call as alpha particle. Now, let me tell you, when these alpha particles, when this helium nuclei, when these alpha particles were bombarded on what? On beryllium and boron, some new particles were introduced. Some new particles were introduced, right? And those particles which were neutral, which did not carry any positive charge or negative charge. Those new particles which were neutral, which did not carry any positive charge or negative charge, whose mass was almost equal to the mass of proton, these neutral particles, whose mass was almost equal to the mass of proton, were termed as neutrons. So basically, when beryllium was bombarded with alpha particle, carbon was produced, and with carbon, this new particle was produced, was emitted basically, right? And this new particle, it did not carry any charge. Its mass was found out to be almost same as that of mass of proton, and this neutral particle was called as basically neutron. In the similar way, when alpha particle is striked on what? On boron, you get nitrogen, and with nitrogen, a particle is basically emitted. This is the same particle basically. This is the same particle which does not carry any charge, right? Which does not carry any charge, and its mass is almost same as the mass of proton. So you call this as basically neutron. So that's only thing which you need to remember about neutron, nothing else, right? So all these things are really important, guys. Again, I'm telling mass of electron you need to remember, charge on electron, mass of proton you need to remember. Mass of proton is 1837 times the mass of electron. Mass of neutron is this much. The charge on neutron is 0. It's neutral. Perfect. Perfect, people. I hope it's clear till here. Now, after the discovery of these subatomic particles, lot of models, lot of atomic models were given, right? And almost all were rejected basically. The first model related to the atom was your Thomson's model. I believe you already know this. This was also called as watermelon model. Now, what did it say basically? This is the simplest among all, right? I said this you should have studied on your own. Anyways, in 1904, Thomson proposed that the atom is a positively charged sphere. The atom is the positively charged sphere in which electrons are uniformly distributed, as the result of which atom is electrically neutral. So basically this Thomson's model, how it looks like. As per Thomson's model, the atom looks like a watermelon. This red colored part is the positively charged, positive charge. This red colored part is the positive charge. And in this positive charge, the electrons are uniformly distributed, as a result of which the total positive charge and the total negative charge in the atom is equal. Therefore, atom is electrically neutral as per this particular model. Right? You call this as watermelon model, plum pudding model, right? Perfect. So my dear students, again I'm telling you, Thomson proposed that your atom, it looks like what? It looks like a watermelon. The red colored part is the positively charged sphere, right? The red colored part is the positive charge, right? In which electrons are your seeds. They are uniformly distributed basically. As a result of which the total positive and total negative charge is equal. Hence atom is electrically neutral as per Thomson. So what was the drawback of this particular model? My dear students, it could not satisfactorily explain the stability of that. What does that mean? That means, see, these seeds are basically the negatively charged. These are the electrons. He could not explain these negative, they can ripple. When they ripple, due to the repulsions, the energy of the atom increases. If the energy of the atom increases, stability decreases, right? If the energy of the atom increases, stability decreases. So he could not explain that part. Why these electrons which are embedded over here, why they do not ripple, right? Why energy of the atom does not increase, why the stability of the atom does not decrease. He could not explain that. And apart from that, one more thing. He could not explain the scattering experiment done by the Rutherford. Now the point is, what is scattering experiment? Let's get to know what the scattering experiment exactly is all about. My dear students, Rutherford, he did one very simple experiment, right? He did one experiment through which we are going to introduce one more term over here. That is nucleus. Let's have a look. What Rutherford exactly did. My dear students, Rutherford, he took a lead block. Over here. This is the lead block which was taken by Rutherford. And in this particular lead block, an alpha particle emitter was kept. And alpha particle emitters are your basically radioactive elements. So basically a radioactive element like polonium was taken in this lead block. Perfect. Now what is going to happen? This is the alpha particle emitter. It's going to emit the alpha particles. These are your alpha particles. And you already know what these alpha particles are. Perfect. So these are the alpha particles which are emitted by this alpha particle emitter. Now, my dear students, over here, I'm going to keep a gold foil. Right? But just to make you understand it in a better way, imagine you're keeping a gold atom over here. This is a gold atom, for example, right? And behind this gold atom, you're keeping a circular screen. And this particular circular screen is coated with zinc sulfide. Imagine It is coated with zinc sulfide. This particular screen is coated with what? It is coated with zinc sulfide, right? It is coated with zinc sulfide. And you know the property of zinc sulfide already? Now, for example, we will try to understand one simple thing. These alpha particles which are coming out from this alpha particle emitter, right? They are made to strike. They are made to strike towards this gold foil, towards this gold atom. And there were some observations. Which Rutherford concluded, right? What were the observations basically? He saw some of the alpha particles, very few alpha particles were getting deviated by very small angles, right? He saw some of the alpha particles, very few alpha particles, they were getting deviated through small angles. He saw majority of the alpha particles, right? He saw majority of the alpha particles cross the gold atom without showing any deviation. And how exactly he saw that? He saw only this part of the screen glowing and this part of the screen glowing. He saw these two parts of the screen glowing basically, right? In the middle, the screen was not glowing. Right? So first of all, what all things he observed? He observed majority of the lines, they were passing the gold atom undeviated, right? A very few alpha particles, they were getting deviated by very small angles. And one of the alpha particle, 1 in 20,000 alpha particles, 1 in 20,000 alpha particles, they deviated at an angle of 180 degree. That means 1 alpha particle out of 20,000, right? It got deviated, right? It reflected back. It came back to the same path. So it showed the angle of 180. It got deviated back at an angle of 180. Now, from these observations, what were the conclusions made by Rutherford? Now, I believe you can easily say the conclusions. The first observation was majority of the alpha particles, they passed undeviated. Very few alpha particles, they got deviated at very small angles. 1 in 20,000, it got reflected back at an angle of 180 degree. Now, people, what can you conclude from here? The first conclusion. Most of the alpha particles, they passed undeviated. Therefore, he concluded the most of the region of the atom, that is empty. Most region of the atom is empty. That's why most of the alpha particles are passing undeviated. They do not deviate at all. Point number 1. Point number 2. Few alpha particles were deviated through small angles, and he concluded atom contains positive and negative charge in equal amounts. So the atom as a whole is electrically neutral. What does that mean? Since very few alpha particles were deviated, how an alpha particle will get deviated? Imagine this is the alpha particle. It's moving, for example. How it is moving in this particular direction. Now, how come it will get deviated from its path? If on the way it finds some charged particles, let's say negatively charged particle is here, one more positively charged particle is here. Imagine the alpha particle is moving in this direction, right? On the way, this alpha particle, it finds negative charge and positive charge. Can you see this negative charge will try to attract it towards itself? This positive charge will repel the alpha particle, right? Since very few alpha particles, they got deviated at some angles, very few alpha particles, they changed its path. Now, what can you conclude from here? You can conclude atom contains some charges, right? Atom contains some charges which are basically opposite charges. Perfect. And they are equal in amount, due to which atom is electrically neutral. The most important thing over here, what is that? Is this particular conclusion. A very few, 1 out of 20,000 alpha particles. 1 out of 20,000 alpha particles deviated at an angle of 180. So what could he conclude from there? If 1 of 20,000 alpha particles, it got reflected back at an angle of 180 degree, he concluded the whole positive charge of an atom, it is concentrated in a very small region, And that small region he called as a nucleus. If you try to understand this, look here. I told you this part, it did not glow. It did not glow. That means just over here, there will be some huge mass which is concentrated here, right? There will be some huge mass which is concentrated here. So Rutherford said the whole mass of the atom is concentrated at the center. The whole mass and the entire positive charge. It is concentrated at the center, due to which the alpha particle, which carries the positive charge, it's coming closer, and as soon as it comes closer, it is experiencing repulsions from this nucleus, which carries the positive charge, right? And the stage comes when it gets reflected back. And this particular small region in which the whole mass and the entire positive charge is supposed to be concentrated, right? Is supposed to be concentrated. This particular small region is something which you call as nucleus. So the major discovery of your Rutherford's alpha particle scattering experiment was the discovery of nucleus. Is this particular point clear to you? Is this particular point clear to you? Right? Since one of the alpha particle, it got deviated at an angle of 180. That means alpha particle is getting deviated. So as soon as the alpha particle comes closer, it will be experiencing some repulsions. As soon it comes more closer, more repulsions. More repulsions means it gets reflected back. And why the alpha particle will be getting repelled? Because the atom should contain the entire positive charge at the center. And that positively charged nucleus basically, that will be repelling the alpha particle, which carries the positive charge, right? Due to which it gets reflected back. Is this clear, people? Let me know once in the chats. Perfect. So I hope you got to know the conclusions made by Rutherford. So my dear students, few more things. After the alpha particle scattering experiment, after the conclusions which were made by Rutherford, right? Rutherford gave one model related to the atom, which he called as Rutherford's nuclear model. And as far as this particular model is concerned, whole positive charge in the atom is concentrated in a very small volume, and this small volume was called as nucleus. Point number one. Size of the nucleus. Size of the nucleus is very small as compared to size of atom, right? In general, if the radius of atom is 10 raised power minus 10 meters, then the radius of nucleus will be 10 raised power minus 15 meters. This is something which he said, right? And my dear students, one result which Rutherford gave to calculate the radius of the nucleus, he said radius of the nucleus is equal to R naught, A raised power 1 by 3 centimeters. This R naught was a constant whose value lies from here to here. And if for calculation purposes, R naught value will be taken as 1.33 into 10 raised power minus 13 centimeters. Sorry. So R naught value for calculation purposes will be taken as this much. What is A? A is the mass number of the atom, right? Whose radius of nucleus is to be calculated. For carbon, A value will be 12. Right? For nitrogen, A value will be 14. So A is just the mass number, nothing else. Right? A is just the mass number. So this is the result by means of which you can calculate the radius of the nucleus. R is equal to R naught, A raised power 1 by 3. Let's say you want to calculate the size, you want to calculate the radius of the nucleus of carbon. That means A value has to be 12. R naught value will take as 1.33 into 10 raised power 1.33 into 10 raised power minus 13 centimeters. And at the end, you will get the radius in centimeters. So this result you have to remember at the same time. So few more points related to Rutherford's nuclear model. As far as the Rutherford's nuclear model is concerned, the electrons are revolving at very high speeds around the nucleus in different concentric circular paths. And these concentric circular paths are called as orbits. So as per Rutherford, if this is the nucleus of the atom, the electrons will continuously keep on revolving around the nucleus in circular paths, right? And these concentric circular paths in which the electron keeps on revolving continuously, these concentric circular paths were termed as the orbits. They were termed as the orbits. Perfect. Now you must be thinking, what were the limitations of this Rutherford's model, right? What were its limitations? My dear students, there is a scientist called as Maxwell. What Maxwell suggested, according to Maxwell, whenever a charged particle undergoes acceleration, it emits radiations. Radiation is energy basically. So it emits energy. So if I talk about what Rutherford said this is the nucleus. And for example, these are the electrons revolving around the nucleus in circular paths, right? These are the electrons revolving around the nucleus in circular paths. If I ask you something like this, imagine the electron is here, right? Imagine the electron is here. What will be the direction of this particular electron? Draw the tangent. This is the direction of electron. When the electron reaches here, this is the direction. It reaches here, this is the direction. This is the direction. As the electron revolves, is the direction of electron continuously changing? The direction of electron is continuously changing. If the direction changes, what does that mean? That means velocity changes due to change in direction. And change in velocity leads to acceleration. So can I say this particular electron right now is getting accelerated? Its direction is continuously changing. It is getting accelerated. And when a charged particle undergoes acceleration, as per Maxwell, it emits radiations in the form of energy. It emits radiation. Radiation is the form of energy basically. So if this electron is being accelerated, it will be continuously emitting energy. If the electron is continuously emitting energy, the energy of electron should continuously keep on decreasing, right? The energy of electron should continuously keep on decreasing, right? So the radius of the orbit should continuously keep on decreasing. And eventually the electron should fall into the nucleus, right? But electron does not fall in the nucleus. Rutherford could not explain this particular point as well. He could not explain why electron does not fall into the nucleus. Perfect? He could not explain that. So this was the first limitation. Perfect? This was the limitation. The second limitation was he could not explain the line spectra of hydrogen. What is line spectra of hydrogen? You will get to know that in the upcoming session. Not now. Okay? Just remember it as such. Remember it as such. Now, my dear students, there is one more important thing. There is one more important thing. Have you heard about distance of closest approach? Distance of closest approach. What this distance of closest approach is all about? See, it's a very simple thing. There is nothing here as well. Okay? See, guys. See, guys. Imagine that you have got the atom and this is the nucleus of the atom. Imagine that this is the nucleus of the atom. The atomic number of the atom is, for example, Z. If the atomic number of atom is Z, that means the atom contains Z protons. If the charge on one proton is E, then the charge on Z protons is Ze, right? So this is the nucleus of the atom, right? I'm assuming that atomic number of the atom is Z. So the atom contains Z protons. If charge on one proton is E, the charge on Z protons will be Ze, right? It is Ze. Perfect. Now imagine here you have got the alpha particle. Imagine here you have got the alpha particle. Perfect. In the alpha particle, there are two protons, no electrons. One proton carries the charge E. So two protons carries the charge 2 times E. This is the charge on alpha particle, 2E plus 2E. This is the charge on the alpha particle. Now imagine this particular alpha particle is coming closer to the nucleus, right? Imagine this particular alpha particle is coming closer towards the nucleus. Now tell me, when this particular alpha particle, which carries a positive charge, if it comes closer, the distance between alpha particle and nucleus, it decreases. If the distance between alpha particle and nucleus decreases, can I say, as the alpha particle goes closer, it will be experiencing more repulsions from this particular nucleus? Absolutely, it will be experiencing more as this alpha particle keeps on going closer, closer, closer. It will keep on experiencing more repulsions due to the nucleus, right? Can I say a point will come, a time will come, a stage will come, since alpha particle is coming closer, repulsions experienced by alpha particles are increasing. I'll say kinetic energy of alpha particle is decreasing. It is decreasing, it's decreasing. There will be a scenario when this alpha particle will momentarily come at rest and will go back in the same direction. Will get deflected at an angle of 180, right? So a point will come, a time will come at which this alpha particle will momentarily comes at rest. And after that, it gets deviated back at an angle of 180. Perfect. I'm talking about that alpha particle, 1 in 20,000, which came closer, came closer. Repulsions on alpha particle is increasing from the nucleus. Kinetic energy of alpha particle is decreasing, decreasing. Stage will come. When this alpha particle will momentarily come at rest and will get deviated back at an angle of 180. Now, my dear students, the distance from this particular point, till the center of the nucleus, the distance from this particular point till the center of nucleus, it is represented by R naught, and this R naught is something which you call as distance of closest approach. Did you get the idea of what this distance of closest approach is all about? It is the distance from this particular point at which the alpha particle momentarily comes at rest and takes a U-turn, right? The distance from there till the center of the nucleus, this is called as distance of closest approach. Now, my dear students, how do we calculate the distance of closest approach? That's the point. That is the point. How do you calculate this particular distance? See, first of all, as the electron comes closer, repulsions experienced as the alpha particle comes closer, repulsions experienced by the alpha particles are increased. The kinetic energy of the alpha particle is decreasing. It is decreasing. It's decreasing. If the kinetic energy of alpha particle is decreasing, that means potential energy of alpha particle is increasing, right? Potential energy of alpha particle is increasing. This is the point at which the kinetic energy of the kinetic energy of the alpha particle becomes 0. And I would say entire kinetic energy has got converted into the potential energy. At this particular point of time, I would say entire kinetic energy of this alpha particle has got converted into potential energy, right? What about the kinetic energy of the alpha particle? It is half of mass of alpha particle multiplied by velocity of alpha particle square. Potential energy. How do you calculate the potential energy? You must be knowing potential energy is nothing. It is K Q1 Q2 divided by R. This is how you calculate potential energy, right? So this is K. What is Q1? Q1 is, for example, the charge in the nucleus. How much is that? That is ZE multiplied by Q2. Q2 is the charge on the alpha particle. That's 2 times E divided by R. R is this particular distance. R is this particular distance, which is basically R naught. Perfect. So from this particular equation, you can say half of mass of alpha particle, velocity of alpha particle square is equal. This is going to be K Z E square divided by R naught. So from this particular equation, you can easily calculate R naught value. R naught will come out to be how much? R naught will come out to be 2 times K Z E square divided by mass of alpha particle multiplied by velocity of alpha particle square. So this is how you calculate the distance of closest approach. This is how you calculate the distance of closest approach. Perfect. And this K already you must be knowing, right? It is 1 upon 4 pi epsilon naught, right? Its value is 1 upon 4 pi epsilon naught, which is 9 in 10 raised power 9, something around that. So this result you have to remember. By means of this particular result, you get to know the distance of your closest approach, my dear students, right? Perfect. And from this expression, you can conclude anything. You can conclude anything. Is this part clear to you? Did you get to know how this distance of closest approach was found out? Perfect, guys. Perfect. Is everything clear till here? So I think this much is enough for today. Perfect. So today you got to know about the basics of everything. Make sure you remember all these basic things. Right, guys? And start making the notes as well. Again, I'm telling you, this particular chapter will be complete in 3 sessions. And one of the session was today, which was all about basics, about the discoveries, etc., etc. I believe all the things are absolutely clear to you. Do let me know in the comment section if you actually like the session or not. Okay? Perfect. Perfect, we will. Hello, with this I'll be taking leave. Do let me know in the comment section, people. Okay? If you got all the concepts.